Hello, I'll be talking about universal limitations on quantum key distribution over network, which is joint work with Siddhartha, Marek Winczewski, and Karol Horodecki. So, starting with the bipartite scenario, if we assume that Alice and Bob share a maximum entangled state like this, just by measuring their A and B systems, they can get log D bits of secure key, which they can then use for the one-time pad. But then there is actually a broader class of states which can be used for this purpose. So basically, it has been shown that there is a larger class of states which are called private states, which are defined like this. You take a maximum entangled state, then you enlarge the Hilbert space and apply some twisting unitary, which kind of makes the entanglement more messy. And then has been shown that if you measure this part here, you can still get a key as long as you keep this part, the so-called shield part, away from Eve. Okay, so this was the bipartite scenario. Now let's go to a multipartite scenario. So we can assume we have more than two parties, let's say K parties, or in this case, 4 parties in the picture, who wish to share a common key. So this is called a conference key. We call this conference key agreement. And again, if instead of a bipartite maximum entangled state, the parties share GZ state, they can just by measuring their respective subsystems get such a conference key. Can log D bits of key from such a GZ state. And again, just as in the bipartite case, there's a generalization of those to some class of states on an enlarged Hilbert states, which are called multipartite private states. Okay, so far I've just talked about the states, but if we have some quantum network, like, I don't know, maybe a quantum internet, we want to distribute those states between different parties. So the simplest scenario in the bipartite case would be just a point-to-point channel from Alice to Bob. So if you're given such a channel, then we can assume that we can use the channel many times. And in between the uses, we are allowed to do free LOCC operations between Alice and Bob. This is here symbolized by the green arrows. And then also Alice and Bob are allowed to keep reference systems. Then this is called an adaptive protocol. And then if you look at the maximum rate at which we can get a private state between Alice and Bob for all adaptive protocols, this is then this private capacity of the channel. And there are a number of upper bounds. One is the TGW bound in terms of squash entanglement, then the PLOB bound in terms of relative entropy of entanglement in case the channel can be simulated using some resource state. And also this result by Castanle, Müller, Hermes in terms of the max relative entropy of the channel. Now, but in reality, we might not just have a channel from Alice to Bob, but we could, for example, have a scenario like this, that we have a quantum repeater where we have 2 channels from Alice to Charlie and from Bob to Charlie. Then Charlie performs some joint measurement and returns a classical message to Alice and Bob. Okay, we can assume that Alice and Bob can keep some reference systems. And then in general, Alice and Bob are allowed to do some LOCC post-processing. Then actually, a similar setup would be used in measurement device independent quantum key distribution, where a setup where Alice and Bob don't trust the measurement which is performed here by Charlie, which is some central relay. And again, it's a very similar setup. And now the idea we had is to include the noisy channels as well as the operation here, which would be in this case a measurement and then some classical broadcasting of the results. The idea was to include this into one map, which we call a bipartite channel, which maps systems A prime, B prime from Alice and Bob to A and B, which go back to Alice and Bob. Then we could also think of just a general bipartite channel where we have just some quantum inputs from Alice and Bob and some quantum outputs going back to Alice and Bob. And we could think of a scenario where we allowed free LOCC between Alice and Bob, and then we can use the bipartite channel multiple times, and also Alice and Bob are allowed those quantum reference systems. And for this scenario, we can again define a private capacity, and in those earlier works, we've shown that we can also get upper bounds on the private capacity of this in terms of this is an entanglement measure of the bipartite channels. It basically measures the entangling power, how much entanglement can this channel create if it's only given separable input states. And of course, what we've shown now is that if we have such a bound, we can just by choosing the right kind of channels, this can also provide bounds for MDI QKD or for quantum key repeaters. Okay, but then I was talking about conference key before, so where we have multiple parties. So then one could think of how to distribute a conference key. So for example, simple scenario would be to have just a channel like this. This is a broadcast channel with one input and multiple outputs, or multiple access channels with multiple inputs and one outputs. Or we could also have a generalization of the scenario we had before of this repeater MDI scenario, where we have the multiple parties send input via those noisy channels. Then there is some joint measurement performed on all of them, and then the classical information is broadcast to all the parties again. Or more generally, one could just think of, instead of a bipartite channel, just a tripartite channel, where we have 3 inputs and then 3 outputs. Okay, so we are thinking what is actually the most general kind of channel that includes all of those different network scenarios. So we thought about something like this, which we call a quantum multiplex channel. So it's a channel which has different kind of users. So we've got aliases A1 to AK, who are both senders and receivers, like in a bipartite channel. So basically they send something and they also receive something. Then we've got Bob1 to Bob L, who are only senders. So they just send something but don't receive anything. And then we've got Charlie 1 to Charlie M, which are only receivers. So they only receive something from a channel, but they don't enter something into the channel. And this is a generalization of point-to-point, bipartite, broadcast, multiple access, interference channels. This is like the most general channel we could think of. And then we were thinking about, again, using the channel many times and interleaving it by free LOCC operations between all parties. And also parties are allowed to have keep reference systems. And then in the end, the goal is that all the parties share a multipartite private state. So we want to do the conference key agreement. And then we have defined a private capacity just as maximum rate of the conference key rate per number of channel users we can get by a general adaptive protocol of this form. And then our main results are upper bound on this private capacity of the quantum multiplex channels. But before stating the results, let me just briefly talk about multipartite entanglement. So basically, if we assume we have some number n of parties, then we can define a k-separable state just as a convex combination of those tensor product of k terms. But then here one should note that unless k is equal to n, in which case this is called fully separable, but if it's less than n, those parties here could differ in the different terms of the sum. Okay. And what is important that for any k, the set of k-separable state is convex. And if k is equal to 2, we call it those states biseparable. And if k is equal to n, we call them fully separable. And if they're not biseparable, then we call them genuinely multipartite entangled. So an example for genuine multipartite entanglement would be a GZ state. And then there is some interesting fact, basically, that we could have several copies of a biseparable state, and then which then become genuinely multipartite entangled. So basically, they say that biseparability is not tensor stable. So we could also use an LOCC to convert several copies of biseparable state into a genuinely multipartite entangled state. So one always has to be careful when one uses more than one copy of a biseparable state. Okay, now our first result is bound on the one-shot private capacity, where we only use the channel one time, the multiplex channel one time. And there, what we use is the fact, what we show, that any multiparted private state necessarily has to be genuinely multiparted entangled. So we show, and then we show that we can construct so-called multiparted privacy test, which is a POVM, which can distinguish which for any state which is close to the private state, this probability is larger or equal to 1 minus epsilon, whereas for all biseparable state, this probability is decreases 1 over d. And then with this, we can get an upper bound in terms of this quantity here, which is defined as the hypothesis testing divergence from the output of the multiplex channel from set of biseparable state, because we have genuinely multiparted entanglement here. And then we take the supremum over fully separable input states. And this is just the hypothesis testing divergence. But then for if we go to many channel uses, we have exactly this problem that we could in principle have a biseparable state, and we take 2 copies and it becomes genuinely multiparted entangled. So for this reason, we cannot consider biseparable state as a free resource if we can take many copies of them. And this is why in our upper bounds, which are of this form, we don't consider divergences from the set of biseparable state, but we have to go to relax to fully separable states. And we get those 2 strong converse upper bounds, which are in terms of the max relative entropy and the regularized relative entropy. Okay, now I think I'm running out of time. Just a few other results which I don't really have time to mention in 15 minutes. One is that if the multiplex channels can be simulated by some resource state and some free LOCC protocol, so-called teleportation simulable multiplex channels, then our bounds reduce to the relative entropy of the resource state. And of course, as special case, as GHZ states are special cases of private states, our bounds also work for distillation of GHZ states. And then we also, instead of looking at channels, we can also just look at some multipartite input state or some multipartite states, and then we want to convert several multi-copies of some multipartite state into a GHZ state or a multipartite private state. So we also look at the rates that can be, we also got bounds for the rates for this kind of state conversion. And we also got lower bounds for like distribution of conference key in quantum networks, which are based on the Devitak-Winter bound. So in summary, we are looking at bipartite and conference key distribution in different network scenarios, and we introduced the quantum multiplex channels, which provide some general framework in which one could phrase many different protocols, such as MDI, QKD, or quantum key repeaters. And would maybe interesting to see which other protocols could be phrased as in terms of quantum multiplex channels, and then we can easily get upper bounds on the conference key or GHZ rate. And yeah, so we have this one-shot upper bound and asymptotic upper bounds. And with this, I would like to thank you for our attention. And here are my co-authors, Siddhartha and Karol. And I didn't find a picture of Marek, so I just put his Facebook picture here. I'm sorry. Thanks.